All right, so the next speaker is Olga Trichtchenko from the University of Western Ontario. And she's going to talk about my favorite subject, 3D waves. All right, so no waste of time. Thank you all, guys, all yours. And sorry about that again.
Yeah, no problem. Sorry, I'm just making sure to hide some of the, okay. Right, so I'm going to talk about using preconditioning methods to speed up some computations for traveling waves. And so thank you so much for the invitation. I'm happy to talk at this. Okay, sorry, I have to. And so hopefully you can all hear me and see my slides. The first thing I'm going to say is that I have a fever today. So if something doesn't fully make sense, it's the fever. It's not the work, it's the fever. And I'm going to also thank my collaborators. So my PhD student, Claudia, she sent me some of the figures actually right before she herself got sick. So we're really doing well here, two weeks into the beginning of our teaching term. But yeah, so Claudia is my PhD student. She did a lot of the computations and sent me a lot of the pictures. I mean, all the pictures you'll see. And also Emilian, who's in the room, who also is a collaborator on this project. And I should probably thank NSERC and other funding organizations. So my outline is pretty straightforward. I'm going to tell you what we're computing and the method, and I'll show you the different models. And then I'm just going to show a lot of pictures in different regimes. All right, so the goal of the work is efficiently and accurately compute solutions for waves under ice. So we'll refer to these as flexural gravity waves in a variety of regimes. And so I'll show you what those regimes are. So again, we're looking for efficiency and accuracy. So we want to be doing this on as large of a domain as possible with as many points, but we don't want the computation to take days. All right, so the schematic is we have ice, which is on top of water, which is underneath here. I haven't really labeled it, but the ice has some small thickness, little d, and the surface is going to be represented by this variable zeta. We're going to look in 3 dimensions. So we have a dependence on x and y. Here I have the bottom to be at minus h, and here I have it flat, but we're going to actually look at some solutions that have some bathymetry in it as well. And so what we're going to do is we're going to use Euler Equations, which describe an incompressible and viscid irrotation of fluid. But the main thing to remember is we're going to work with this potential formulation where the velocity potential is going to be given by phi. And we're going to have a variable surface, which is given by zeta. And so it's going to be under a sheet of ice. And we're going to be looking at 3-dimensional solutions. So here we have Laplace's equation, 2 conditions at the surface. And the main thing to note is that in the Bernoulli condition here, we have terms that have to do with flexural rigidity, this D. And P flex is going to describe the type of model that we use for this ice. And then we're also going to have a moving load, which will represent as little p in here. Later on, actually, I think capitalize it because the moving load, we're going to go into the frame of reference that's moving with it. So it's going to no longer depend on time. And then we have a condition at the bottom. So this condition will also vary when we're looking at the bottom having some sort of topography. So again, rho is the density of the water. D is the flexural rigidity, which we can assign to be, we're going to vary what this D is. We're going to vary what the model that we use. And we're also going to look at different types of loads, moving loads on the ice. Okay, so the term modeling ice is very idealized. We're going to assume that it's a thin elastic plate and that the ice bends with the water. So there's no trapped air or anything like that. We're going to assume no friction between the ice and water. And then we're also going to assume that this ice, the ice layer, the elastic sheet is going to be continuous. So we're going to assume that it doesn't break. But again, in theory, we should be looking for when does it break. But in terms of the modeling using these PDEs, we're going to assume a continuous sheet. So the coefficient of flexural rigidity is really, you can write it in terms of the Young's modulus, the Poisson ratio, as well as the thickness of ice. So at some point, we're going to vary what this D looks like. And we're kind of assuming that we either don't know fully the parameters for Young's modulus or Poisson ratio. That is, they might be different throughout the ice. So the ice sort of has some heterogeneities. This little d, the thickness of the ice, We can also say that, for example, imagine if the ice thickness varies. Okay, so what we're going to do is we're going to assume the simplest model for now for ice, the p-flex term. We're just going to write it down in terms of the biharmonic model. Really, it's going to be 4 derivatives in x of that free surface, 4 derivatives in y, and a cross derivative term. The important thing to note really is this fact that there's 4 derivatives, and so that's the difficulty really, is that if we're discretizing it, solving it numerically, there are these 4 derivative terms that we have to make sure we're very careful with. So to illustrate the methodology for computation of these types of waves, we're going to look at traveling waves generated by moving pressure. The pressure is going to move in the x direction on ice, and it's going to, we're going to look at different regimes. For example, the load is varying, so different pressure distributions, load distributions, as well as different load speeds. We're still going to assume that we have traveling waves, so we're going to not have a variable speed load for now. We're going to also vary our flexural rigidity. So what happens if ice is, for example, heterogeneous, so if the thickness changes or any of the parameters change in the ice. And we're going to briefly, I'll show you some pictures when you add, for example, viscoelasticity. So adding viscosity, to the model. And then I'm going to describe what happens when you have varying bathymetry. So accounting for the fact that you might have some topography at the bottom. All right, so the method of solution, I won't show you, but how to write down these boundary integral equations. But essentially, if you need more details, there's lots of experts in the audience, for example, Emilian. And so what we're going to do is we're going to work in terms of the free surface zeta, and we're going to write down the velocity potential, which is evaluated at the surface. We're going to call that Q. And so if we reformulate everything in terms of just the surface variables, zeta and Q, we get these 2 equations. So I might refer to this first equation as the local equation because it only contains derivatives. It doesn't contain any of the integrals. And the important thing to note here is we have this capital P. It's really unfortunate naming because of 2 different capital P's. But this capital P, first one, is going to represent our moving load. And then the second, that P flex, is going to represent the type of model that we're using for ice. So whether we have viscosity or not, whether it's a viscoelastic model or not. And D again is the flexural rigidity. And here you can introduce different parameterizations of it. So here's this type of a parameterization where we have F, the Froude number. And then the second equation that looks a little bit like a Green's function for a Laplacian, except for we have this variable surface zeta that shows up. And so what happens with this, in the integral, we have these kernels K1 and K2 that we're integrating over, which have this D in the denominator. And this D could potentially go to 0. So we have to make sure that we treat it in a way where we don't have any singularities or the denominator decaying to 0. So we need to also desingularize this model. And the other thing that I'm also not showing here is that you can also assume some symmetries, for example, in Y. If your load is moving in X, you might have symmetry in Y. In some cases, you can also assume there's symmetry in X. So you can introduce, instead of integrating from -infinity in X and in Y, you can start to integrate from 0 to infinity. And the other thing to note really is this term is going to lead to some dense matrices, because you have to essentially, to compute something at just one point labeled star, you have to integrate over the entire domain. So if you want an equation for one point, you have to consider all the other points in your domain. So it's going to show up as dense matrices. And to get the most accurate solution, you have to consider as large of a domain as you can in X and Y, because you're integrating from -infinity to infinity. So that also becomes important in terms of looking at how accurate the method is. All right, so what we're going to do is we're going to introduce equally spaced points. So they have n points in X and m points in Y. And there's different ways to introduce what your unknowns are. In this case, we've chosen to label, or to have the unknowns be the X derivatives of the surface, the variable surface, as well as the x derivatives of the velocity potential. You can have unknowns as the y derivatives, or you can have them just be the variable surface and the velocity potential. But what this way of choosing our unknowns is going to look like is that at some point for our boundary integral equations, we're going to need terms that look like zeta or terms that look like q. So we're going to have to integrate an x, and those are going to show up as little triangles in our matrices. And I'll show you what I mean in a minute. And what we're going to do is then we're going to also introduce finite difference methods to discretize the derivative. And then really we get 2 times m equations. Really, there's a couple of extra equations from the boundaries of the domain. And the other thing to note is that we have fourth derivative terms. And so we have to use really a 13-point stencil if you are using, for example, a centered difference method. So really you're going to need a lot of points in your domain to try to compute that flexural contribution. So you really have to be careful with that term, and then you have to figure out what's the best way to compute these fourth order derivatives at the boundaries. So that's also not trivial. And so a general method for solving a nonlinear set of equations, so this is just a very general method, is you have some initial guess, and then you can use, for example, a Newton-like method. So you really solve the system. The Jacobian, which depends on your nth iteration, times this correction term delta, is equal to that set of equations. I evaluate at your nth, and then at your nth iteration, and then you really set your n plus first iteration based on your nth one. And you can introduce this term lambda to say how much you want to correct your nth iteration by. And so you're going to iterate over this. And the most computationally intensive part is really computing this Jacobian, and then really computing the inverse of that Jacobian is really the most computationally intensive part. And so that Jacobian involves taking the derivative of all the equations, so 2nm really plus a few extra terms for the boundary, 2nm equations, partial derivative with respect to all the different unknowns in your unknown vector. So if you want to keep a lot of terms in your domain, this is going to be a very large matrix. You have to compute its inverse if you want to use a traditional Newton method. And when I showed you that boundary integral method has that double integral. So really it's going to lead to very dense matrices. So what we're going to do is we're going to use an iterative Krylov method to construct the solution, which relies on matrix vector products instead of doing a full inverse to construct, to solve the system. And to help this iterative Krylov method converge faster, we're going to use a preconditioner. So really this preconditioner is just going to allow us to make sure our Jacobian is better conditioned. And really this methodology was introduced in this paper, the Jacobian free Newton Krylov methods. In there, they actually even use GPU acceleration for computing nonlinear ship wave patterns. And so what we've done is we've modified it to include effects of ice, as well as the different regimes. All right, so here is the algorithm, this Newton Krylov method with the preconditioner. So what we're going to do is really we're going to solve the system where J is multiplied by this P inverse. So this term in red should really look almost like an identity matrix if we picked our preconditioner correctly. And so if we introduce this P inverse, we have to have this P here multiplying that little correction term. So we're going to solve this kind of, this iteration instead. And we're not going to be computing the full inverse. We're going to be constructing it based on matrix vector products. And so what does the Jacobian really look like for the problem? So this preconditioner P is introduced such that the Jacobian resembles P inverse. And so let's see what the Jacobian looks like before we talk about what the P inverse term looks like. So the Jacobian, for example, from the linearized problem with just a free surface, so no ice, has this dense component, which comes from that double integral. This component here really has that free surface description. And here you see the little triangles is because our unknown variables are the x derivatives, and really we want to compute the free surface itself. If you add ice, for example, this term here starts to fill in a little bit because you have those 4 derivative terms. And then if you're looking at the the Jacobian for the nonlinear problem, so once you know what your solution looks like, you can write down the Jacobian, you start to see that you actually have more terms filling in the bottom left. But really these terms are, so here that scale represents the order of magnitude of the terms. So the darker the terms, the larger in order of magnitude they are, and the lighter they are, the smaller they are. So really this filling in of the Jacobian is going to be by smaller magnitude terms. So hopefully if you choose a good enough preconditioner, it won't really matter that the nonlinear problem has also these terms present in there because they'll be smaller. So hopefully multiplying the Jacobian by that inverse of the preconditioner, you'll still see that you get almost like the identity matrix. And so the way to figure out how good a preconditioner you have is look at, for example, the eigenvalues. So if you look at the spectrum for the Jacobian of the nonlinear problem without the preconditioner, you see that you can plot the real versus the imaginary parts of the eigenvalues. You can see that the real go from -30 to roughly 40, and the imaginary parts go from -50 to 50 roughly. So it's not so poorly conditioned, but it's not ideal because essentially you want these real parts of the eigenvalues to look like 1 if you're trying to approximate that identity matrix of the preconditioner. So if you look at the preconditioned system that's now on the right-hand side, you see that multiplying that Jacobian by that preconditioner, you actually get that your eigenvalues are closer to the real part equaling 1. So there's a bunch that have clustered here. They don't have a very large imaginary part. And then really, they don't go much above 3. So really you've reduced the order of magnitude of the eigenvalues, the real part of the eigenvalues, and you've reduced by 2 orders of magnitude, really the imaginary part. So this, for example, is using the inverse of the Jacobian as the preconditioner for the linear problem to precondition the Jacobian of the nonlinear problem. And so what happens is if you compare these preconditioned methods to traditional methods involving computing for the inverse of the Jacobian. So we just used Python's routines. So for example, if you look at these Newton-Krylov methods, so if you have, for example, just a numerical preconditioner, so you're not computing any part of the preconditioner analytically, it'll take you 8 hours to generate the Jacobian. The time it takes to solve the system is really just very fast here. So this is hours, minutes, seconds. So hours, minutes, seconds. So very, very fast. So this mesh is 80 by 40. For using this hybrid preconditioner methods that my student came up with, where some of the preconditioner you compute analytically based on the linearized model, and some of it you compute numerically, the time to generate the Jacobian is a lot faster. So you're going to use that Jacobian as the preconditioner. And then the time to solve is still order of seconds. So the total runtime is minutes. And then if you're looking at traditional methods, for example, using fsolve, it's going to take you hours to solve the whole system. And if you introduce a preconditioned Newton-Krylov method, it's going to take you minutes. So really, we were able to reduce the runtime from hours to minutes by using these new preconditioned Newton-Krylov methods for computing waves under ice. And so to generate the preconditioner, as I mentioned, the biharmonic term requires 13-point stencils to represent the centered difference scheme. And so if you want to test a variety of conditions, if you want to see what to do with the boundaries, because the terms with the 4 derivatives really take a, they need a lot of points on the left and right of where you're trying to compute the derivative. And it's going to really result in very long analytical expressions for the flexural term. But luckily, it's not a very dense contribution to the overall structure of the Jacobian. So you can actually just do this part numerically. So you can account for the flexural contribution to your Jacobian numerically. And then the rest of the preconditioner, you can generate it from just the free surface waves, so gravity waves without ice. So you can have that contribution analytically. You can keep that, you can store it, and then you can modify all the different regimes that you're looking at for ice numerically. And so this free surface preconditioner using the analytic form was really done again. You can see it for details in this paper. And then this hybrid preconditioning method, if you want more details, we also have a paper on that. Okay, so finally the pictures. All right, so imagine you have, again, your Euler equations. I'm not showing the boundary integral form, but you have the Euler equations. And I'm saying what happens now if your pressure looks like, which looks like it only depends on, it doesn't depend on time, and you vary it. So that's a moving load here. So for example, it's of this form, so it looks like an exponential. And what you're going to do is going to vary the width of it, or sorry, the length of it really, because it's moving in the X direction. So you're going to say, imagine I have a very condensed car versus a truck or something else traveling on ice. What's it going to look like? Well, on the right-hand side, you actually can see the different profiles that you get when you look at the cross-section. So we've normalized this pressure so that the area underneath gives you the same answer every time, even if you're varying the size of it. And so you can see how the different profiles compare if you're looking at the cross-section in X, and then you can look at the cross-section in Y. And from this, you can even compute the strains for the different types of vehicles, for example, to see sort of which one is going to generate the largest strain and more likely to break the ice. So then you can look at the fully three-dimensional profiles. So here they are. This is just when the pressure is has the same, it's basically rectangular. So it's the same Lx as Ly. So here you're making Lx, so you're making it longer in the direction of propagation, or on the direction that your load is moving in. You're making it longer, and you make it longer. You make it longer so you can see what's happening here. The pattern is spreading. And then this is the longest we can make that moving disturbance without running into issues at the boundaries. So here's what that looks like. So you can compute this no problem. And the interesting thing about this is for this varying pressure, you don't even need to modify the preconditioner. So you can generate that preconditioner with the flexural term in it, and then you don't have to worry about what happens when you're changing that load. You can also compute, for example, these non-localized wave patterns. So these are waves under ice. So this is when the speed of the moving load is larger than that critical speed. And then you can go on and you can say, okay, well, imagine now instead of varying this P, we want to vary D. So either our ice has varying thickness, or the parameters like the Young's modulus and things vary in ice. So you can do that. So here we had to introduce something that was continuous. So you can see, for example, if you introduce some varying D in the X direction, you can introduce the fact that your wave patterns then become asymmetric. You can introduce things like sinusoidal patterns for a D. You can do the same trick in Y. You could say, imagine, for example, inside my ice is thicker in the middle of a lake, or imagine it's thicker at the edges. And then you can do the same game here. You can introduce a cosine pattern. And then you can do things like you can add viscoelasticity. So you modify that P flex term to include this tau F contribution. And then here again, we're looking at traveling waves. So we're not taking full advantage of the time dependence. So you can add that. You can compute the different viscoelastic regimes by varying this tau F. I'm sorry, I'm rushing. I have to join another Zoom meeting as well. So yeah, so you can add it. It's no problem. The time that it takes to compute these solutions, again, is not, it's still in the order of minutes. And then the other thing you can do is you can also look at variable bottom. So introduce this extra equation for what happens to your velocity potential at the bottom, which we'll label as beta. What this is going to do is, I'm also not including all the set of equations. You still have a few conditions to satisfy for the boundary. So there's an extra equation here, but I'm leaving out two more equations that you have to have. You can, again, rewrite it in terms of the boundary integral reformulation. It's a bit more complicated. And in fact, we're still making sure that it makes sense for the different types of bathymetry that you can do to the bottom topography. And really the vector of unknowns is going to be made up of three different sets of terms. So the variable surface, the velocity potential at the top, velocity potential at the bottom. So what you're going to get is the Jacobians that are these 3x3 block matrices. So you have quite a few more contributions from that are dense matrices here. So if you can imagine, this definitely increases your computational time, but it still takes minutes anyway. And you have to find the right preconditioner, which obviously includes a whole extra row and column. Here, actually, this is shown for a free surface, so no ice here. But if you had ice, this area would fill in. But you can include that ice contribution numerically. And then you can look at, for example, what happens if you have a bump on the bottom. So this is what your surface would look like. And the bump here is described by these parameters. So it's a very small bump to make sure your boundary integral formulation still makes sense. Or if you have, for example, a crater on the bottom, where the crater is described by this beta. And so, yeah, let me just post the conclusion. I know I've rushed through this, but essentially what you can do is, using this preconditioned Newton-Krylov method, where with the preconditioner, we compute using a hybrid method where we account for the flexural component numerically, and the gravity waves, so the free surface waves with no ice on top, you can account for analytically. You can see that this reduces the computational time from more traditional methods from several hours to just a few minutes. And you can examine different regimes for the pressure, varying flexural rigidity to represent possible inhomogeneities in ice. And you can add more physical effects, such as using a viscoelastic model or bathymetry, for example, if you have a variable bottom. All right, thank you very much for your attention.
Thank you very much, Olga, for the very nice talk. I know you're in a rush, is that right?
Yeah, but I mean, if you have, there's a quick question, actually, direct them to Amelia, and I have a fever, can't answer them anyway.
Just wanted to check. All right, so we have time for maybe one quick question from the audience. All right, so maybe one quick question from me. Do you use some high performance computing resources for your computations, or you're just running this on a laptop?
So you can run it on a laptop. My graduate student has been using our cluster, which lives on campus. But I think even if she runs the comparison chart, I believe, and she can chime in, I think she's on there, is that comparison chart was still done on her laptop, I believe. Wow. So it still takes minutes on her laptop.
Yes, it does. Yes, that's true.
Thanks.
I did all of this on my laptop.
Wonderful. How many CPUs on the laptop? Yeah. Is it an Apple or Dell?
It's not a very fancy laptop. I don't remember, but it's not like, top of the line, or anything. It's just sort of mid-range computer.
MacBook Air or Pro?
It's a Lenovo computer.
All right.
ThinkPad.
Okay, so all right, so I think that's all. Thank you very much, Olga, for a very nice talk. I would also to thank Colleen earlier. So I think that's it for the afternoon session today. The rest of the afternoon is free. We still have the tea break. So we thank the speakers again one more time. Thank you. Have a good day. Bye-bye.